everyone, welcome back. In this video, we are going to go through a very hairy looking derivation, but one that actually is rather simple. And where we are going with this derivation is to really understand where the idea of equilibrium and our equilibrium expression really is coming from. And this is working towards understanding reactions and kinetics and all of the pieces that chemists love to play with. Okay, so I showed you this last time in the last video. I just wanted to remind you, we can define this weird little symbol that we're going to call a C. That's not actually its real name. I don't actually know what its real name is. But we're going to define this as the extent of the reaction. And what this means is really how much has this reaction progressed. And so based upon stoichiometry, we can say if we know how far the reaction has progressed, we should be able to calculate the number of moles of any reactant or product that is in the solution at that point in time. And the algebra for showing that is just that the moles at some point in time is equal to the moles at time 0 plus this mole ratio times the extent of the reaction, so how far we've gone. So if we start at y0 here, as time goes on, we are going to add moles. And so if we say that the reaction has proceeded to this arbitrary point, that we can get the new number of moles of our system at that point. And since the component y is a product, the amount is increasing, and so we are adding. Whereas over here, A is a reactant, it's being used up, and so we are subtracting the moles that react. This is really just a fancy way of showing stoichiometry. Okay, so this is just a checkmark question. The boxed equations show the amount of species in the chemical reactions it shows that they do not change independently from each other. And the question is, why is this? And our options are the balanced chemical reaction, conservation of matter, conservation of energy, or both A and B. Well, the answer really is A and B, and that's just because B tells us that A has to happen. If we didn't have conservation of matter, we wouldn't have balanced chemical reactions. Okay, so we talked about this last time in the last video. The Gibbs free energy of the system is a function of temperature, pressure, and the number of moles of each of our components in our reaction. And so we can say that dG is given by this big long equation. This is basically what we worked out in chapter 7, where we said that dG is equal to minus SDT plus VdP plus mu dN. And what we are being specific about here is specifying mu dN for each of our species. And remember that mu is our chemical potential and N is the number of moles. So now if we suppose that we perform the reaction at constant temperature and pressure, which is a very common way to running reactions, we come up with what we got, where we left off in our last video, where dg is equal to really just the sum of the chemical potentials and the number of moles, times the change in number of moles. Okay, now, so we can redefine our change in number of moles based upon this extent of the reaction. And so this is really just saying that as the reaction proceeds, A and B decrease, and Y and Z are products, and so the number of moles increase. And so we can plug this new expression of the this is the stoichiometry, this new the stoichiometry times this extent of the reaction. We can plug these in to our dg equation. So we are just replacing dn with this new term because they're equal to each other. And we get this sort of extent of the reaction. And with some rearrangement, we can get that basically that the delta G of reaction is equal to these are products and these are reactants. And so we basically get the stoichiometry times the chemical potential of the sum of the products minus the sum of the reactants. I know this is written in a little bit of a funny notation, but it really is the chemical potential of products minus reactants. So really, physically, this delta G of reaction represents the change in the Gibbs energy when the extent of the reaction changes by 1 mole. So what does that mean? That's saying that if we started with 2 moles of A and some infinite amount of B, the reaction would progress until we used up 1 mole of A. And so we can think of this really as moles of reaction, because if we use up 1 mole of A, we're going to use up some moles of B, and we're going to form some moles of Y and some moles of Z. And so really the Gibbs energy is this extent of the reaction. Okay, now, we've kind of been dancing around what this chemical potential is. Let's take a moment and help us understand the chemical potential a little bit more deeply. I'm still not confident that I'm going to provide you a good definition for it, but this might help us a little bit. The chemical potential is pressure dependent. And so the reference pressure for the chemical potential is 1 bar. So if we are working at anything other than 1 bar, we have to correct. We have to provide a correction term for this chemical potential. And that correction term is this integral VDP. And really, you can just think of this as taking this chemical potential that is for an idealized system at 1 bar, and we are adding a correction term, or so we're putting it into the real world. And so with some algebra, we can get that the chemical potential mu at some temperature plus RT ln of P is our corrected, our real chemical potential. Now, with this, let's think about which of the following did not go into the evaluation of the chemical potential. A, we treated the system as the ideal gas. This is true, we did, because to plug in for V here, we used that V is equal to nRT over P, and that's how we got this RT integral of P. B, P star or P naught equals 1 bar, so we do not always explicitly write it. That is true. That's how we ignored this P naught whenever we simplified the equation. So if P naught is 1 bar, we don't have to actually write it. We treated the pressure change as reversible. And we treated the temperature as being constant. We definitely treated the temperature as being constant because we have T here as a constant. And so this tells us that we did not treat the pressure change reversibly. And so this means that this is a generally true situation, that we don't have to think of this as a reversible situation, that this is always true. Okay, so now what are we going to do? We're going to do some more substitutions and some more algebra. We're going to make this delta G expression that we had simplified down. We are going to plug in the fact that now we know that our mu is equal to mu naught RT ln of P. And we're going to plug that in to our expression for delta G, giving us this very complicated expression. Now, in blue, these are the chemical potentials at temperature temperature T, and the reference point pressure of 1 bar. And in this kind of maroony color is the effect of changing pressure to the partial pressure of the gas. And so now remember that partial pressure is really just the pressure of one single gas within a container. So if we have, if we have our container, and inside of this container we have several different gases, the total pressure is going to be based upon the collisions of all of these gases with the walls of the container. The partial pressure would just be looking at one of the gases. Okay, so now if we assume that the gases can be treated as ideal, we can do some algebra and get to this expression, which I'm not convinced is really any simpler. But what we have basically done is we have sorted out our stoichiometry times our chemical potentials and our natural log of pressure terms is really all we have done. Some plugging and chugging and some rearranging. So now what we're going to do is we're going to use our log rules, and we are going to realize that these pressure terms can be simplified down into this RT ln of P raised to the nu of these are products over the reactants. And we still have this expression that we have seen before. This is delta G. And it turns out that we can define this ratio of the pressures, we can define those to be Q, the reaction quotient. And this is one of the most important equations in general chemistry. And this is probably an equation that if you have taken biochemistry with Dr. Chamberlain, that she has basically tried to tattoo onto your brain. And what we have is that delta G of the reaction is equal to delta G standard plus RT ln of Q. So this delta G standard, this delta G naught, represents the standard change of Gibbs energy. So changing from reactants to products in their standard states at standard temperature and pressure. So this in red is the standard conditions. And in blue is this RT ln Q. In defining Q, we defined that pressure equals 1 bar. That's key. But this becomes sort of a correction term. Because remember that we started with our ideal chemical potential, and we corrected that chemical potential based upon pressures. And based upon those pressures, we came out with this Q term. And now we can finally get to where we're going. If we say that at equilibrium, Gibbs free energy is at a minimum, and so the Gibbs free energy is not changing with the extent of the reaction anymore. Remember that we talked about how G versus time went to a minimum, and down here was equilibrium. And that is where we can say that the change in Gibbs with respect to the extent of the reaction is equal to 0. And so if that's the case, then that means that this whole term, this delta G standard plus RT ln of Q, is equal to 0. And that allows us to rearrange and find that this delta G standard is equal to minus RT ln of now K. So at equilibrium, this Q expression is equal to K. And so we can replace Q in this expression, and we get that delta G is equal to minus RT ln K, where K is what we call the equilibrium constant. And with that, we now have derived what the equilibrium constant is, at least in terms of pressures. Now, remember that we often do this in terms of concentration, but we will get there. For now, let's just keep it in terms of pressure, and we will continue working with this concept.